Everyone. Thank you for joining me for my talk, which is about representational connectivity analysis. So traditionally, functional connectivity has been evaluated using a kind of summarization of activity from within ROIs. So you get activities from ROIs, whether they're vertices or voxels. Then you summarize them into a single value, and you have different conditions as shown here. And then what you do is to try to see how these vectors of different conditions, which can be time or your conditions of the task that you have, and then try to see how these vectors of activations match between the two RIs so that you can some sort of infer connectivity across RIs. But there has been a kind of recent shift towards evaluating all the information within ROIs, within the voxels or vertices within ROIs, to see if there is any information that you're missing. In order to do that, representational connectivity analysis has been introduced. And this method evaluates all the interactions or similarity between your conditions and put them in a matrix called representational dissimilarity matrix. And in this matrix, you can see the geometry of representations within your ROIs about different aspects of the task that you have. And then what you do is to check for similarities between the RDMs that you obtain from different areas of the brain. So you look for shared information between ROIs using these RDMs. So we call them model-free representational connectivity analysis, or model-free RCAs. But there are two other methods of evaluating representational connectivity analysis, which are one model RCA, in which you try to see how information is represented within each ROI based on a hypothesized model. So you evaluate the correlation between your model, between the neural RDMs and the model RDM that you have hypothesis for, and then evaluate how the correlation matches to the correlation between another ROI and the same model, and infer connectivity if these two ROIs match the same model, or whether they are similar to a common model. Then therefore you can get information about how they share information about what you are looking for. And a third method can be two model RCA, in which you try to see if there is correspondence between your RIs and its specific hypothesized model. So you evaluate the correlation between the neural RDM within an RI and the model that you think should be represented in that RI, and then you evaluate the connectivity between that correlation and another RI with its corresponding model. So in this way, you can somehow obtain information about whether there is a kind of transformation of information from one area to another, because they represent two different things, but you have two different hypotheses for the two ROIs and can check for potential similarities between them. So we simulated a scenario in which we had different categories of objects, semantic categories of objects presented on different spatial locations on the screen. So there are two aspects of information represented here. Semantic categories as well as spatial locations on the screen. So we get, based on the literature, we think that position information or the location information should be represented more dominantly in early visual areas compared to semantic information, which you can more dominantly find in inferior temporal cortices. So we guess that we hypothesize that these two information should be represented across the two ROIs, which based on these RDMs, you can see that they are negatively correlated to one another, meaning that they are reflecting two opposite, some sort of unrelated aspects of information. And then we generated neural RDMs based on the hypothesized information that should be presented there. So you can still see that information is uncorrelated or negatively correlated across the two ROIs. So in the first simulation, we tried to see if having models in your representational connectivity analysis can put lenses on the connectivity that you're measuring. For that purpose, we have some illustration here. So we know that the RDMs can be represented as vectors in the space, and vectors can have different angles relative to one another. And the angles somehow represent the correlations that we measure in reality. So you can see that ROIs can have, for example, if two ROIs, ROI1 and ROI2 have 90 degrees difference, it means that they are like orthogonal to one another, and they do not show a high correlation to one another. But if you have a model in between the two ROIs, you should see connectivity between them if you are using the model-based connectivity analysis. So from the viewpoint of model-free RCA, you do not see these two ROIs being connected because they are orthogonal to one another. But when you look at them from the viewpoint of a model, you can see that these two ROIs can be somehow related to one another. And on the other hand, there can be cases where two ROIs are somehow related to one another because they have less than 90 degrees of correlation angle between them. But when you look at them from the viewpoint of a model, you can see that, for example, here ROI2 is orthogonal to model RDM, so that it means that from the viewpoint of the model, ROI1 might be related to the model, but ROI2 no. So from the viewpoint of a model-based RCA, it gives you negative result about connectivity, meaning that there is no connectivity. As opposed to model-free RCA, which tells you that the connectivity exists. So we simulated this scenario, and imagine that we have a model which contains information about both regions, which I explained to you before. So two different aspects of information which are not correlated to one another, so meaning they are uncorrelated. But from the viewpoint of a model which has components from both regions, you can see that the correlation are positive to this model. And from the viewpoint of this model, while model-free gives you negative or no connectivity between the two, it might be the case that the two ROIs are correlated to the model, meaning that they might be considered connected. You can implement model-based representational connectivity analysis in different ways, and this conceptual point can affect your results in different ways. So our recommendation would be to check for both model-based and model-free connectivity analysis before deciding on whether the connectivity should exist or not. And use simple models for which you are confident that information, that your model doesn't have information which are not connects the two regions which are not dominantly representing information that you're looking for. So the second simulation, we try to see if common patterns or noise can affect your results about connectivity and can spuriously give you information about connectivity, suggesting that connectivity exists. And we wanted to know how RCA is affected by noise. So we added noise to both regions. So you can see the representations in both regions, which were not correlated to one another. But when we added the noise, the two regions became correlated. And this suggests that from model-free RCA gives you spurious connectivity because the two regions have been correlated to one another because of the additional noise. And when you evaluate them against each other, you can see that the noise gives information about connectivity. But and also one model RCA. When you have a model and you correlate two regions and you have the same model in there, because the two regions are correlated already and you have a common model, the two become also correlated to the single model that you have in there. But if you use two model RCA, you can see that if two regions were already uncorrelated, you added noise, they become correlated. But you have two distinct models for the two regions for which you have hypotheses. It means that the two regions, although correlated, they do not become correlated. Because you evaluate their correlation against two models which are uncorrelated from one another. You do not pick up connectivity because two models are not correlated to one another. So we tried to investigate more and see how uncorrelated should ROIs be not to be affected by noise. And what we saw was that the more the two regions are correlated to one another, the more they are prone to be affected by by common patterns such as noise. And here we suggest that if you have hypotheses for two regions which should represent two different aspects of information, you can use two model RCA to not be affected by additional noise to the areas. And this result implies that ROIs with similar representations, such as V1 and V2, for example, are more susceptible to noise or common patterns in which you are not interested in if you're using two model RCA. But regions which encode two different aspects of information, they might be less susceptible to noise or unwanted patterns that you are not interested in. So in the third simulation, we tried to simulate a situation where information appears in the first region and is sent to another region. Although the two regions are representing two different aspects of information, we believe that information should go from the first region to the second region and transforms on the way to the destination. So we hypothesized here, we wanted to know if two model RCA allows us to pick up that kind of transformation of information. In order to do that, we simulated a situation where the first area shows the representation, and then the second area after delay, which we call the congruent case, in which information appears in the first area and moves to the second area. And we wanted to know how we can pick up this kind of pattern, like transformation from the first region to the second one. And what we saw was that model 3 cannot pick up that connectivity, which we were expecting, simply because two regions are processing two different aspects of information. And when you correlate the two RDMs directly, you cannot pick up that information transfer, simply because the RDMs oppose one another. And when you have one model RCA, still you cannot pick up the information because one model does not allow the transformation to be picked. And also, but interestingly, if you have two models for the two regions, you have clear hypotheses for the delay and everything, which we already had for these two methods as well, you might be able to pick up that kind of transformation information from one area to another. So these results suggest that we can pick up information about connectivity, even if information is transformed from the first area to another, if you have hypotheses for the delay between the two areas, which also determines the direction of information flow. And if we do not have hypotheses, what if we do not have clear hypotheses for the information which is dominantly represented across ROIs? In that case, it's better to use nonlinear functions which allow you to pick up a statistical relationship which are not necessarily linear between the source and destination areas. So take-home messages would be to model-based RCAs or models within RCAs can help you pick up different types of targeted aspect of connectivity, but they should be used with caution. Common patterns or noise can be avoided if you use two model-based RCA and the two ROIs are distinct and different enough. And two model RCA allows you to pick up the transformation of information from one area to another. So the MATLAB scripts are available and the paper is submitted as a preprint. And I would like to thank you for your attention and my collaborators for their support in this book. Thank you.